These days, these Fridays.
How much weight did you get? 11 times.
So the first slap hits in the morning. Mondays, Wednesdays, what?
Someone sitting there or another here? Oh, that's just a right. Yeah. Here, instead of me passing these out, I'm going to pass out this, but you're going to want, this is like a template that we're going to be using pretty much daily for the rest of the semester almost. So there's 500 I printed. Like, they'll be gone in a week. So come up and grab like 10, 5.
Yeah, hey Joel, grab like a staff.
Remember, I still have next hour. Don't take my old file.
She just wouldn't grab the whole like an inch and a half of them.
Got it.
You're going to give me some of those back, right?
Not yours.
Emily, yeah, I was going to give everybody something to feel good.
Hey, a couple more.
I grabbed the stack.
Mr. Davis. Make a double-sided.
No, last time they'll write the problem back.
Oh yeah, alright. I was gonna say, or else Mikey called Rod because he gave us a pack of this big, each person of a chapter, and didn't make a double-sided. So it was like probably 200 pieces of wasted paper.
Getting this out first. And I crossed off most of the stuff I meant to cross off, but I forgot to cross off this one spot. So right here in the question where it says different from, cross that off and write less than. So this is called a significance test. This is what we're going to be. So we're done with basically 60%, I'd say, of the material, maybe 65. And the last part, there's only like 2 main topics. So if you look back there, that chart is basically, we have this a little more to do after that, but that chart is basically like each of those boxes is a chapter, pretty much. So the 2 concepts you have to learn are significance tests and confidence intervals, and once you learn them, you can apply them to different situations. So really, once we learn one thing, it kind of just repeats, and the formula changes. When it repeats, the formula changes. When it repeats. So the process main kind of stays. Yeah. So I'm gonna read through that part. Do that. Read through that. So, what we got is a population that claims, you don't have to write this, I'm just kind of explaining like the main concept of what we're doing. That claims that mu is 12.1. Well, then we take our sample. So this should get narrower. And what's x bar going to equal? 12.1. Well, remember, this is like all of the possible samples. So we're taking samples of size 4. 4, I think, in this one. So every hour, someone fills 4 cups. And so if we took all of those, then we take those 4 cups and find the average of those. And that was one of the spots in this graph. I take 4 more, and there's just boxes falling down. And every box represents its own sample. And when you stack up the samples, they make this shape. Well, I got, in this case, 12.05. So 12.05 is probably like right there. If we're supposed to be at 12.1, and we get 12.05, does that throw off alarms to you? Like, wait a minute, something's not working here. We're supposed to get 12.1 and we're only getting 12.05, or is that just kind of like, it's pretty close? I'm asking your opinion. I think it's pretty close. If it's supposed to fill up 12.1, you know, you put your thing in the thing at McDonald's, supposed to give you 12.1 ounces of Coke or whatever, and you get 12.05, like, I'm not going to go complain. I'm not going to say I think it's broken. To me, that's within, like, the normal range of where it should be. If I filled it up and it got, like, you know, there's 6 ounces in it, does that throw off alarms? Something's probably wrong, right? So there's a great, so 12.05, I think we're fine. 6, we're obviously probably not fine. What about like 11.9? What would it depend on? What else would I have to know to think about this? What if it's 12.1 and my standard deviation is 0.0001? Then would 11.9 concern you? Yeah, because that's like a ton of standard deviations away, right? But what if it's 12.1 and the standard deviation is 2? Then does 11.9 concern you? No. So there's a couple things you got to figure, and it's all just like, is it far enough away that we're going to say, yes, there's something wrong? Or are we going to say, no, there's nothing wrong? So there's this interesting thing where you can't say something's true. You can only say it's false, or, yeah, it's not false. I can't necessarily say something's true. We'll get into that more as we go. But so that's the whole point of this. We're going to try and see, like, this is where we should be. Are we within that range, or are we not within that range? So we're going to do the problem on here. And I'm going to kind of do this backwards. We're going to do this actual problem. And then I'm going to follow it up and make like a general guideline template that you can use for any problem. So we'll do the specific problem first, and then I'll make you like a cheat sheet kind of. So this is a 1 sample t-test for me. So there's going to be a lot of stuff in here that you're like, I don't even know what the hell he's doing. I'll tell you that up front. But the point is, I'm trying to give you the big picture first, and then we'll kind of narrow in on what it all means. Okay. So the first thing you have to do is define the variable that you're working with. So I'm going to say that mu equals the mean amount of juice for the population. That's what I want to know about. I have information from 1 sample. I'm going to try to use that 1 sample to see if there's something really wrong with the process. You know, if my sample comes out to be 6, I got 6 ounces of Coke, that tells me there's probably something wrong. Okay, H sub 0. That's supposed to be H naught. It's called the null hypothesis. Let me back up a second. We're going to do a specific one. Then I'm going to give you a general one. Then I'm going to give you a packet of notes where we can like break down what all this stuff means. So you don't have to take notes on breaking down what all this stuff means when we're going through this. That's what I'm getting at. Okay. So the original claim, the null hypothesis, is what the claim is. So they're saying that the mean is 12.1. We always start off by assuming that they're right. So we're going to say, okay, status quo, I think everything's fine. I think it's what it should be. HA is called the alternative hypothesis. That's what we think. Thanks. That's what we think might, like they're saying 12.1, but I kind of feel like it might be less. I feel like they're pretending they're giving me more coke than they actually are. So then I'm going to say I think it might be true that the actual amount, the actual average of the population is less than 12.1. I'm trying to base this off one sample. But if my sample come out to 6, I'd be pretty sure that the actual population is less than 12.1. Right. The second box, you're putting the check of conditions. So there's 3 things that we're looking for here. One is that we can use the t-distribution. I know that you don't know what that is yet. That's one of the things I'll follow up with, and we'll kind of break down what all this stuff is. There are 3 ways that you know that you can use the t-distribution. So you need one of these. You need a normal population. Oh wait, this is supposed to be the specific example. Okay, yeah, then we have enough. We're good. We're there. Normal population is stated in the problem. Sorry, I started to do like the general. That should be like that lowercase t, not a capital T. That really matters. But. We need there to be an SRS. So does the problem tell us there's an SRS? Simple random sample. It says randomly. Doesn't really say simple random sample, so we're going to say problem states random. We need a little bit more than that. So I'm going to put assume SRS. And the third thing is that we don't know, so the population standard deviation is unknown. Okay, in the math box here, I should mention this too. You can use this for all the practice ones you want, but when you go take the chapter test or the actual test, it'll be a blank sheet of paper, right? So these are like, this will help you, and by the time you take a test, this will be in your head so much it won't even matter that it's blank. You'll just like see those spots, I think. Just keep that in mind. All right, so this is always going to be test statistic equals statistic minus parameter. So remember, where does the statistic come from? The sample or the population? The sample, and the parameter comes from population. Divided by the standard deviation of the statistic. And that applies for all. That's just z-score. That's the z-score formula, because z-score is x bar minus mu over standard deviation. That's just statistic minus parameter. This test statistic general pattern holds true for all of those. So once you know this pattern, like that formula, you can kind of plug in. In this case, our test statistic is t. Again, I know you don't know what it means. I know this is kind of confusing. Just kind of like following through without knowing. What is the? How do I represent the statistic if I'm dealing with means? What's the letter representation? X bar. How do I represent the parameter if I'm dealing with means? It's mu. And then what's the standard deviation of a sample mean? Divided by the square root of n. So this is like what we did last chapter. Is like this right here is basically what last chapter was for. That's the main point of it. All right, now we can put numbers in. Finally. So that's just like all kind of general stuff. What is x bar in our problem? Perfect. 12.05. Because that's the one from the sample, right? The mu is 12.1. And the standard deviation is 0.085 and then divided by what? Divided that is a standard deviation from a sample. They didn't say this.
Right, so since the sample wasn't already technically like had been divided by 4.
I shouldn't have ever showed you that problem. No. Just roll with it for now. Just roll with it for now, please. Okay, calculate that. What'd you get? That seems right. When was negative wrong?
Something needs to change because like your whole like the whole scenario is like it's positive and it's like the first half.
Does anybody else have a clue what she's talking about?
You have to hit her. Just end her conversation.
Shut up. No, like when we did like
Yes. Yep. I totally remember that.
shut up. It was like the second chapter. It was like get a negative number and then like you know how you're trying to find like the situation to change or whatever. Like so I'm right. Shut up. I don't know.
Okay, Kayla.
So I'm just gonna say that. Do you know what you're talking about?
I'm not exactly sure what you're talking about, but I don't think, like, what this T is just trying to say is this is basically just trying to get the Z-score of where it is.
That's what I'm talking about.
It's negative. Why just say Z-score on
Well,
the
but
curve?
so what does a negative z-score mean?
That like I don't know.
No, it doesn't mean it's wrong. It just means you're below the mean.
Yeah. But then like don't you want to be above it though?
Not necessarily.
How about we just keep
Okay.
flowing
You
here?
just want to flow it.
Okay.
Did other people get this number? Because that's not what the. I just. Did you get negative 1.176?
Yeah, that's kind of.
Oh, wait. One second.
Did you get negative 1.176?
I trust her.
Hey.
I could actually plug
You
in.
never trust me with okay, so when was the last time I was in my grade class? Let's be honest.
Yeah, I got negative 1. Okay. Okay. So that's the next thing I was going to say. Is just talk, so what does that mean? We're below the mean. We're about one standard deviation below the mean. Does one standard deviation below the mean like make you think it's something crazy, or does that seem like within kind of the typical range? Seems within the typical range to me. If you get, and there's a way to calculate it, but if you got like a negative 10 here, well now our bottle of Coke was 10 standard deviations below what it was supposed to be. Does that kind of raise your eyebrows? Like, wait, there's something going on here. So like, where's that cut point? One standard deviation doesn't concern you. 10 does. Well, so where's the? That's what I got to show you. Okay, so I'm gonna sketch this, and you do want to sketch these on your. Like this is part of the answer is the sketch. So I'm gonna say mu equals 12.1. That goes in the middle there. Over here is where my sample was. So x bar in this case is 12.05. Is that big enough for you guys to see? Are you still not getting it, Athena?
I'm working on it. We'll find out in a minute.
Hit her. Come on.
I think you're making her nervous.
I don't know. I don't want to like rush you, but I don't want to move on without you either.
I'll
So.
figure it out. Go ahead.
All right. So over here is t equals negative 1.176. What we're gonna do is find this shaded area, the size of that shaded area. We're gonna do that over here. But I'll do it in a second. But think about that shaded area is very small, does that make you think that the original claim is wrong or okay? If this shaded area is really small, if it's really small, so this T, like, how would it be small? If this were like way over there, right? So if this were way over there, wouldn't it be like more standard deviations away from the middle?
Yeah.
So something's probably more wrong. So the smaller this area is, the further away I am from the mean, and the more I'm like, okay, wait, something's going on here. If it's big, the bigger it is, like if I put it like right there, you know, it'd almost be 0.5. If it's big, I don't think anything's wrong. So that's what's called a p-value. No hat, just p-value. And there was normal well, there is normal CDF, right? Where you can find like if this is normal CDF, I would go negative 999, comma 12.05. Like I could do it with normal CDF. I could figure out the problem. This isn't normal. This is what's called a t-distribution, which is like similar to a normal distribution. We'll get into what it is and why that happens. But in your calculator, you want to type in t-CDF. And I'll show you where it is. Negative 999, negative 1.176. You also need to type in 3. Can anybody tell me where the 3 came from? It'd be kind of hard to tell, I guess. You can try. It's 1 less than your sample size. This is what's called your degrees of freedom. You are going to label that. I know you don't know what's going on. It's okay. I know. That's all right. So TCDF, if you just go second dister and scroll, it's number 6. Like the same place you would find normal CDF or binomial CDF or geomet, you know, in that same menu. So I get 0.162. So almost every year there's at least boxes there, or 9 I guess. One of those they'll choose and make it a free response. Then the other ones still make up like a large portion of the multiple choice. They'll just pick sections. So they would say like, here's your situation, find the p-value. You don't have to do the whole process. You can just kind of jump to that spot. So let me show you on your calculator. Your calculator will do this too. I'm not going to show you how yet, but just to show you what that looks like on your calculator. So that's what we just drew basically, right? And then at the bottom it's telling me, okay, we're 1.17 standard deviations below the mean, and our p-value, the size of this is 0.16. If I shaved the whole thing, what would it come out to be? 1, right? And then again, if this moves over, what happens to my p-value? It's smaller, which makes me more or less likely to think something's wrong. More likely to think something's wrong. Okay. We're almost done. At the beginning of this problem, I should have told you what alpha was. I didn't. Right now, write down alpha, which looks like a Jesus fish.
Looks like a what?
Jesus fish. Alpha equals 0.05. Have you seen Jesus fish on like bumper stickers?
Yeah. Oh. Yeah. What? I mean, Jesus fish.
Okay. So now think about what I was talking about with the shaded area. Our shaded area was 0.16. This alpha is like your cutoff. So if our p-value, if our shaded area, which is just p-value, comes out smaller than that, this is the cutoff point. Remember I was saying like, well, if you get 6 ounces, you obviously know something's wrong. If you get 12 ounces, you obviously think something's fine, but like 10, I don't know, is that too weird or is that not? This is how you determine the cutoff point. They'll give you this in the problem. if our area is smaller than this, does that make me more or less likely to think something's weird?
That's like normal.
If my area is smaller than this bar must have moved over this way, which makes me more likely to think something's weird, right? If my area is larger than this, I don't think anything's wrong. Like so my cut point is kind of over here somewhere. And I'm not that far enough away yet, so I don't think anything's wrong.
But that changes from each problem.
Yes, it's almost always 0.05, but they can make it 0.01, 0.1. But they'll give it to you. You don't have to come up with that on your own. So, I'm going to conclude this, and I'm going to say since our p-value is greater than alpha, then I'm going to reiterate. So 0.162 is greater than 0.05. I'm just summarizing. And this is the part that you're going to have to learn some more about. We fail to reject H0. You can't see that far?
Do it the other way and
What did I draw the other way?
nothing I do it the other way.
Can we just say accept, not fail to reject?
We cannot. So here's the thing. So that's a huge issue. So I got this vending machine that I think when I put a cup on there, it pours out 12.1 ounces of Coke, right? Well, I go and it pours out 6 ounces of Coke. Can I say the machine's broken? Yes. I go, this is one sample of 4 times. And out of those 4, I got an average of 12.05. Is that enough to convince me the machine is not broken? I think so. Is it enough to convince me that the machine is giving exactly 12.1 every time? No. So I can't say that the 12.1 is right. I can just say it's probably not wrong.
Oh my gosh.
That make any sense?
Yes.
That's a big like conceptual thing to understand. Yeah.
So this one is.
Bring it on. What do you got?
So say you take a sample size of 4, and then so the meat is basically 12. You get like 2 6s and then 2 18s. Those still even out to be 12. So then what do you do?
Well, the reason that would our standard deviation there would be huge, and that would like play into it, and that would help. But that also gets the idea like bigger sample size. So okay, here's another example. There's this person who's always telling me how smart they are. So I'm going to get 35 in the ACT, 35 in the ACT, 36 they say. I'm going to get 36. I'm the smartest math person there. Okay, great. Here's the ACT. They got 35. Is that enough for me to call them a liar? Like, you don't know math, you're not going to get a 36? No. But is it enough for me to, but I also at the same time, is it enough for me to believe them and say, yes, you get 36? It's kind of that gray area where I'm like, I'm not going to call you a liar, but I'm not going to call you a truther. So, what's that from Rick and Morty?
No, it's Josh.
I've never even seen it, but every year I teach this, so it's like people bring it up.
It's in these paper shows.
Okay, so does that answer your question? So we fail to reject HO. There is not enough evidence to say that cups are being underfilled. You're just putting it in context. An hour. So I know there's a million questions on that. Yeah, I wouldn't even know where to start. So let me go through what we're going to go through. Get out another blank one. We're going to do like a general template. So like this would be the notes. And what a lot of people do, some people there's going to be like 13 of these by the ends. I would put them all in one spot. So this is like the most important thing you do in this class, probably. So put them all, like some people have laminated them, which is a little bit excessive, but it also kind of is cool. I mean, so, yeah, right there. So this is a template. There will be like I said, like 13 of these, and it's really important. So I would keep it in a spot where like I know where all of those are. All right. So this is a template for a 1 sample t-test. Yes.
Just let you know that at 11:20, a bunch of people with online
Oh,
classes
yeah.
are.
Oh crap! I got it.
I forgot about that.
How many people is that?
I didn't even know that.
I guess we got 7 minutes to finish then.
Oh no.
This won't take long. This is just copying stuff down. I'm not going to try to like explain stuff while I'm doing it. So you always set equal to the population mean, and you put it in context. Please don't write literally in context. I swear, every year someone, like in the previous problem, someone would write mu equals population mean in context. Like you're supposed to use the context of the problem. Don't literally write the words in context. HO will always be that mu equals something. Like we have to start off with a certain assumption. The problem will give you that. Like the last one was 12.1 because we're supposed to get 12.1 ounces of coke. HA is always going to be either greater than, less than, or not equal. So if they're going to say, we think this is true, I'm going to say, wait a minute, I think it's bigger, or I think it's lower, or I think it's different. I don't know if it's better or worse, but I just think it's different. Your conditions. For a t distribution, you need one of the 3 things. A normal population, or a large sample size, and the cutoff, that there's no real reason for this, the cutoff the AP test came up with was 30. It's not like anything magical happens at 30, they just kind of needed a number. So anything over 30 is considered a large sample. In about 90% of the problems, one of those 2 things will cover it, and you can just like write that down. Occasionally, they'll give you one that's like a size of 10, and they don't tell you the population's normal, and then you have to actually make like a dot plot. It's just annoying. Like you're already doing this giant process, they make you do a dot plot in the middle of it, but occasionally it does happen. So sometimes you have to say dot plot shows no skew or outliers. The second thing is an SRS must be stated or assumed. So like in that last one we wrote down, problem says random. We have to assume it's SRS. And then I'll be honest with you, the AP test only requires those 2. I'm requiring a third because it makes people remember this last portion of it. The population standard deviation is unknown. How long is that meeting?
It's probably like 8 minutes.
It's like 20.
It's short. It's not like.
It's not at all hours.
All right, and then in the math box, you're always going to write down the general pattern, the general formula I put at the top of the last one. So test statistic equals statistic minus parameter divided by standard deviation of statistic. That'll go in that box for every single one of these that we do. And in this specific one, t is going to equal x bar minus mu divided by the standard deviation divided by the square root of n. Then Then you put in the numbers. So I'm just putting like numbers in these spots. And then you get a t-value. The p-value will always equal TCDF from low to high, comma n minus 1, and you label that n minus 1 as degrees of freedom. And that gets you a p-value. Yeah.
Can you just put DF or do you want us to put? Because on the calculator it just says DF.
Yeah, I'll look at their answers and see. I can't remember. Every year someone asks this, and every year I look, and then every year I forget. Then you make a sketch. And the sketch can look a lot of different ways depending on if it's greater than or less than or not equal. So I'm just kind of doing like one example here. So you put what mu is, you put what your x bar is, you put what your t is, and then this shaded area, I like to draw a line there to like kind of let them know I understand that the size of this shaded area is my p-value. You're going to have an alpha that they'll give you. You just need to write it down. Two options for the decision. Since p-value is greater than alpha, and then you like verify that with numbers. You fail to reject HO. There is not enough evidence to support HA. So just copy this down before you even comes out. Copy the second one down before you leave. The other one would be since p-value is less than alpha. Again, you have to like kind of reiterate that and be like, here, look, right? Remember there, look. We reject H9. What's up, Zach?
Is that H or HA and then I see it now.
Which one?
I got it.
Okay. Since p-value is less than, we reject HA, and now we would say there is enough evidence to support HA. So, this is weird because I just spent an hour teaching you stuff and you probably don't know anything. That's fine. We'll hopefully fix that in the next couple days.
That's cool. It's job security.
Right. But like, don't freak out that you don't know anything. You're really not supposed to. It's just setting the